This is a technical presentation for ECEN 160, Fundamentals of Digital Systems, Lab 2. First off, as an introduction, my name is Mike Summers. I'm the one on the left there. Just a little bit about me. I'm a software engineer major. I'm from Idaho Falls, Idaho. Some of my interests include oil painting, spending time with my family, and playing board games. My thesis for this presentation is Boolean equation simplification, knowledge of universal logic gates, and familiarity with available integrated circuits can help us develop low-cost, efficient digital systems. In the process of working through Lab 2, these points were clearly illustrated. We were first provided this truth table and asked to produce the associated non-reduced Boolean equation. Looking over the table, we can easily extract this equation. Now, of course, we can go on to produce a simulated logic board with this equation, and it would look something like this. Obviously, this is a less than optimal solution, so we're going to have to do something about that. Let's start with our equation. The first step is to reduce it to its simplest form. We have a few tools to choose from that will help us with that, such as Boolean algebra laws and theorems, Karnaugh Maps, or we can simply use software. For this example, let's use a tool that was recently introduced in the course, Karnaugh Maps. As a review, to populate our Karnaugh map, or K-map, we first list our minterms from the truth table and fill them into the map, making sure to follow the pattern dictated by the enumeration of the minterms according to gray code. Once we fill in our K-map with the correct variables, we can continue to group together the clusters of ones. Remember, a grouping is valid if you can connect orthogonal groups in sets of 2, 4, 8, 16, etc. To create the most reduced equation, we are to circle the largest groups that we can, keeping in mind that the map wraps around from side to side and top to bottom. Thus, the ones in the corners here can actually be grouped in a cluster of 4. We then look at the common elements in each of these groupings, separating them with an OR, and come up with B0 and D0 or C0. So let's see what progress we've made so far. We can already see a significantly more efficient solution here with our reduced equation, so this simplification has already taken us pretty far. Let's go ahead and use integrated circuits to get a clearer picture of what a circuit board would really look like. In this case, we'll need 3 types of ICs since we've got 3 types of gates. The 7404 component would take care of our NOT gates, or inverters. The 7408 takes care of our AND gates. And finally, the 7432 takes care of our final OR gate. However, before implementing ICs into our simulation, let's back up and consider the concept of universal logic gates, or functionally complete gates. Remember that a NAND gate is precisely such a gate, meaning that with some rewiring and combination of NAND gates, we can use them exclusively to functionally replace inverters, AND gates, and OR gates. With a bit of reworking, we can actually redo our simulation with all NAND gates. Now that we've made this conversion, let's jump forward once again to the step of implementing ICs into our model. So this single 7400 IC happens to contain 4 NAND gates, precisely what we need to finish our simulation. So, to review, we started with this simulation from our original equation, and we're able to create this much more slick implementation through Boolean equation simplification, which we did with the K-map. An understanding of universal logic gates helped us use only NAND gates in our solution. And finally, knowing that a specific single integrated circuit held all the NAND gates we needed, we were able to finish off our solution in a much more efficient design. As a reminder, these were the points listed in our thesis. So, why should I care? How would this apply to a real-world situation? Well, if you were tasked to design a circuit board, your employers would obviously want a design that would reduce the needed hardware, the space used up on the board, and the amount of energy consumed to operate the product. Basically, when you can reduce those factors, you can create a smaller system that has the same functionality. If you consider that perhaps hundreds of thousands of units may be produced, the cost savings for the company really add up. Also, a product is more marketable to the consumer. For example, a lower priced product can be provided. Consumers care about things like that, along with product size and battery life. All of these factors are affected by a designer's ability to effectively design efficient digital system solutions. With that, I'll conclude this presentation, and I thank you so much for watching.